Imagine a world where machines can heal themselves, adapt to their environment, and even evolve over time. This isn't science fiction, it's the fascinating reality of biological nanomachine hybrid systems, or BNHS, a field at the cutting edge of innovation. These remarkable constructs blend the intricate machinery of biology with the precision engineering of nanotechnology, creating something entirely new. Imagine tiny biological robots, woven from DNA and protein, working tirelessly to repair damaged tissue or even build sustainable infrastructure for the future. BNHS represent a paradigm shift in our technological capabilities. They are not merely machines that mimic life, they are living machines capable of growth, adaptation, and even a rudimentary form of consciousness. This fusion of living and non-living components opens up a world of possibilities, promising solutions to some of humanity's most pressing challenges and needs. But how do these living machines actually work? What are they made of? And how do they operate in real-world scenarios? In the following sections, we'll delve into the fascinating world of BNHS, exploring their intricate architecture, the mathematical equations that govern their behavior, and their potential to revolutionize our world in ways we are only beginning to imagine. To truly grasp the marvel of BNHS, we must take a closer look at the intricate architecture that makes these systems so unique. Each BNHS is a masterpiece of bioengineering, designed with precision and purpose. By breaking down their structure, we can begin to appreciate the complexity and ingenuity behind their creation. Picture a beautifully complex tapestry, woven from 5 essential components: scaffolds, energy cores, command modules, growth nodes, and healing agents. Each of these elements plays a distinct and vital role, working together in perfect harmony to bring the BNHS to life. Let's start with the scaffold. This is the structural backbone of the BNHS, much like the skeleton in a living organism. It provides the essential support and shape, ensuring that all other components have a stable foundation to build upon. The scaffold is often constructed from meticulously arranged DNA strands or intricately engineered proteins. These materials are chosen for their strength, flexibility, and compatibility with living tissues. The scaffold acts as the framework, allowing the other components to be precisely positioned and securely attached, much like beams and girders in a skyscraper. Next, we encounter the energy core. Think of this as the beating heart of the BNHS, the source of all its vitality. Without a reliable energy supply, none of the other components could function. This tiny powerhouse is often fueled by glucose or similar biomolecules, mirroring the way living cells generate energy. The energy core converts chemical energy into usable power, driving every process within the BNHS. Without it, the system would be inert, like a car without fuel or a heart that has stopped beating. The energy core doesn't just provide power, it also regulates the flow of energy, ensuring that each part of the BNHS receives exactly what it needs, when it needs it. This careful balance is crucial for maintaining stability and efficiency. The command module is the brain of the operation, encoded with specific instructions, often in the form of synthetic DNA sequences or advanced biocircuitry. It directs the BNHS's actions and responses. This module interprets signals from the environment and coordinates the activities of all other components. It's responsible for decision-making, adaptation, and even learning, allowing the BNHS to interact intelligently with its surroundings. Growth nodes are the builders and repair crews of the BNHS. These clusters of specialized cells or engineered molecules drive the system's ability to grow, adapt, and repair itself over time. Growth nodes are essential for maintaining the machine's structural integrity. They respond to stress, damage, or environmental changes by generating new material, reinforcing weak spots, and ensuring the BNHS remains robust and adaptable. Finally, we have the healing agents. These microscopic repair crews, made up of enzymes or other biomolecules, constantly patrol the BNHS for signs of damage or wear. When they detect a problem, they spring into action, repairing broken structures and restoring function. This gives the BNHS its remarkable self-healing capabilities, allowing it to recover from injuries that would cripple ordinary machines. The seamless integration of these 5 components, scaffold, energy core, command module, growth nodes, and healing agents, allows the BNHS to function as a unified living machine. Each part supports and enhances the others, creating a system that is both resilient and intelligent. Together, their combined efforts create a system that is far greater than the sum of its parts. The BNHS is capable of extraordinary feats of adaptation, resilience, and even a rudimentary form of consciousness, pushing the boundaries of what we once thought possible in biotechnology. The behavior of BNHS, while seemingly complex, can be broken down into elegant mathematical equations. These equations serve as the language through which we can describe, predict, and even influence the life cycles of these remarkable living machines. By translating the intricate dance of biological and mechanical processes into mathematical terms, scientists gain a unique window into the inner workings of BNHS. These dynamic life equations govern the growth, adaptation, and overall lifespan of these living machines. Each equation captures a different aspect of their existence, from how they gather resources to how they respond to challenges in their environment. The interplay of these formulas forms the foundation for understanding how BNHS thrive, struggle, or decline. One such equation is the biogrowth/collapse equation. This formula, based on principles of biological growth and decay, predicts how the BNHS will expand or shrink over time. It allows researchers to model the rise and fall of populations, and to anticipate when a system might reach its limits, or enter a phase of rapid change. Variables in this equation include the availability of resources like energy and building blocks, as well as environmental factors like temperature and pH. Even small changes in these variables can have dramatic effects, causing the BNHS to flourish or falter. Scientists must carefully monitor and adjust these parameters to maintain stability and promote healthy growth. Understanding this equation is crucial for controlling the size and lifespan of BNHS. By simulating different scenarios, researchers can predict how the system will respond to resource shortages, environmental stress, or sudden changes in conditions. This knowledge is essential for designing BNHS that are resilient and sustainable. Another key equation is the recursive adaptation rate. This formula quantifies the BNHS's ability to adapt to changing conditions. It measures how quickly and effectively the system can sense its environment, process new information, and implement changes to its structure or behavior. It takes into account factors like the rate of environmental change, the sensitivity of the BNHS's sensors, and the efficiency of its adaptation mechanisms. The more responsive and flexible the system, the higher its adaptation rate, and the better its chances of surviving in unpredictable settings. A high recursive adaptation rate indicates a machine that can rapidly adjust to new situations, a critical trait for survival in dynamic environments. This adaptability is what allows BNHS to overcome obstacles, recover from setbacks, and seize new opportunities as they arise. These equations, though complex in their full form, provide a powerful framework for understanding and predicting the behavior of BNHS. They enable scientists to move beyond trial and error, using precise models to guide their experiments and innovations. By manipulating the variables within these equations, scientists can fine-tune the performance of these living machines, optimizing their function for specific tasks and environments. In this way, mathematics becomes not just a tool for analysis but a creative force, shaping the future of BNHS and unlocking new possibilities for life engineered by human hands. The true marvel of BNHS lies in their ability to mimic the fundamental principles of life: adaptation, self-healing, and navigation. These are not just technical features, but the very essence of what makes living organisms so successful in the natural world. By drawing inspiration from biology, BNHS engineers have created machines that blur the line between the artificial and the organic, opening up new possibilities for robotics and automation. These principles, often taken for granted in the biological world, are breathtaking achievements when replicated in engineered systems. The challenge lies in translating the complexity and subtlety of nature into mechanical and digital forms, a task that requires both scientific ingenuity and creative problem-solving. Recursive adaptation is the BNHS's ability to learn and change based on its experiences. Unlike traditional machines which follow rigid programming, BNHS can modify their behavior in real time, responding to new challenges and unexpected situations. This dynamic learning process allows them to thrive in environments that are constantly shifting and evolving. Through a constant feedback loop between its sensors, command module, and growth nodes, the BNHS can adjust its behavior and even its physical structure in response to environmental cues. This feedback system is inspired by the way living organisms sense and react to their surroundings, allowing the robot to become more efficient and effective over time. Self-healing, a hallmark of living organisms, is equally impressive in BNHS. When damage occurs, the system doesn't simply shut down or require external repair. Instead, it initiates a sophisticated internal process to restore itself, much like how a living creature heals a wound. Damage, whether from external forces or internal wear and tear, triggers the release of healing agents. These agents are specially designed materials or nanobots that can identify and target the affected area, beginning the repair process almost instantly. These microscopic repair crews work tirelessly to rebuild damaged structures, ensuring the BNHS's continued survival. Over time, this self-healing ability reduces maintenance costs and extends the operational lifespan of the system, making BNHS not only more resilient but also more sustainable. Finally, BNHS navigate their surroundings with remarkable precision, using a process called symbolic resonance navigation. This advanced method allows them to interpret complex environments, avoid obstacles, and find optimal paths, even in places where traditional navigation systems would fail. By emitting and detecting specific signals, they can map their environment and pinpoint their location with remarkable accuracy, even in complex and dynamic settings. This capability is crucial for tasks that require high levels of autonomy, such as search and rescue missions or exploration of hazardous areas. These three principles, working in harmony, allow BNHS to function with a degree of autonomy and resilience previously unseen in engineered systems. The integration of adaptation, self-healing, and advanced navigation means that BNHS can operate independently, recover from setbacks, and collaborate with other machines to achieve complex goals. They are the key to unlocking the full potential of BNHS, enabling them to perform complex tasks and adapt to unpredictable environments. As these systems continue to evolve, they promise to revolutionize industries ranging from manufacturing and healthcare to disaster response and beyond, ushering in a new era where machines are not just tools, but partners in innovation and survival.